Hi there, this is Peter Banworth Carrillo. This is our first lecture video for STAT 243 online. So the way these lecture videos are going to work is I'm going to type up lecture notes as I talk about the concepts. I recommend that you watch the lecture video before you start your homework and you refer to the lecture notes as you work through your homework. It's also important that you use your textbook to help you triangulate or fill in some of the gaps that I may not hit during my lecture. So to access your lecture notes in this video, you go to the home page on Canvas, scroll down to the week, and you should see a link for the lecture notes here, which will open a Google Doc. And by the time you watch this video, you'll also see a link for this video as well. When you go to the lecture notes, it should just open a Google Doc in Drive that you can access, that you can look at, but not edit. And then I will just talk through my lecture notes as I type them up. And here we go. So this is lecture notes, chapter 1, Introduction to Statistics. I'm going to cover some basic ideas from statistics and study design. First idea is types of data. There are two main types of data: quantitative, which is numerical data, and qualitative. By the way, Google is getting predictive, so you may see sometimes that as I type, it actually guesses what I'm going to write next. Sometimes it's right, sometimes it's wrong. Quantitative, which is numerical data, and qualitative, which is non-numerical data. So quantitative data. Examples would include temperature in degrees, height in inches, age in years, length in centimeters, etc. Quantitative data has numerical content. There are numbers associated with the data that have meaning. Qualitative data. Examples include color, city, let's see, true or false questions, yes or no questions. It could include things like types of beverages, soda, water, milk. These data have no numerical content. You don't number colors, blue, green, red. And even if you did, the numbers wouldn't have any true meaning. Saying blue is 1 and green is 2 doesn't mean that green equals blue plus 1. So those are our two main types of data. Within each type of data, we have subcategories. So on the quantitative side, quantitative data can be classified as continuous or discrete. Continuous data can be measured at any value in a range. For example, temperature can be measured to be 0 degrees, 10 degrees, 8.6 degrees. Technically, it could be measured at 72.3195684 4 degrees just because we never measure the data at that level of specificity. Or I should say, we may never measure the data at that level of specificity, but technically we could. Discrete data takes on certain numerical values that do not include a whole range. For example, numbers of games won in the Premier League. A team could win 0 games, 5 games, 6 games, but a team cannot win 6.5 games, let alone 3.4, 6, 5, 9, 8, 2, 1 games. It is easy to see which teams win more games because that data is numerical. A team with 3 wins has more wins than a team with 2 wins. Those are the ways that I like to classify quantitative data, continuous and discrete. There's 2 other ways that they aren't additional ways, they're a different way to slice it. So a different way to classify quantitative data is interval versus ratio. Interval data has an order, but not a relative size. For example, temperature data has an order. 50 degrees is hotter than 30 degrees. But we wouldn't say that 60 degrees is twice as hot as 30 degrees. I mean, we might think that kind of colloquially, but from a numerical standpoint, it's not really twice as hot. 0 degrees isn't even the lowest temperature against which we measure our data. Right? There's such things as negative 15 degrees is possible. So we can order our data, but we don't really talk about relative size, about something being twice as big or twice as small. Ratio data has an order and a relative size. For example, games 1 has an order, 5 games is more than 3, and it has a relative size. 8 games is twice as many as 4 games. There is a 0, a baseline against which we can measure our data. By the way, when I type as I talk, I tend to get a little robotic. My apologies. You'll notice I'm not typing right now. To myself, I sound a little more human. Also, I haven't recorded these videos before. I don't know how long they're going to take. Feel free to pause whenever you want. You can pause and go back. Everything should be captioned. And most of what is important, I'm going to be typing down, so you should be able to see it in your lecture notes as well. Interval data can be continuous or discrete. Ratio data can be continuous or discrete. So it's not really a one-to-one match. It's just a different way to classify quantitative data. All right, we've talked about quantitative data completely. Let's switch now and talk about qualitative data categories without numerical content. Again, we can classify our qualitative data in a couple different ways, subcategories. Can be classified generally into two categories. One is labels, and which is nominal, and the other is, I'll say, ordinal, rankable. So nominal data is purely descriptive. There is no natural ordering to the data. For example, colors. Blue, green, right? If we did a favorite color, it would be blue, green, red, white, etc. There is no ordering to this data. Blue is not more than green. Another type of nominal data that we're going to work with a lot is called binary data, which means two possible values for the data. Yes, no is binary data. True, false is binary data. Success, failure, or heads, tails. These are all types of binary data. There's one possibility, or there are two possible values for the data. There's no such thing as yes, no, maybe in binary data. Often we encode binary data as 0 and 1 to make our statistics easier. However, binary data has no inherent numerical content. Saying true equals 1 and false equals 0 does not mean that true is bigger than false. Okay. The other type of qualitative data is ordinal data. This is data that has no inherent numerical content, but can be ordered or ranked. For example, the most common example is the Likert scale, which asks you a question like, how useful are statistics in your life? And you can answer not at all useful, somewhat useful, or very useful. We could imagine putting those in order, but they don't have any inherent numerical value. Somewhat useful is more useful than not at all useful, but it is not twice as useful. It is not 7 units more useful, etc. Every once in a while, I'm going to take myself a break, which is basically me pausing the recording. So if you notice that things seem a little bit different, that's what's happening. It's going to happen right now. All right, let's talk about our next topic from Chapter 1. Our next topic is types of statistics. There are two types of statistics that we're going to study in this class. The first are descriptive statistics, and the second are inferential statistics. So descriptive statistics describe a set of data so that we can understand the data better. Examples would include something as simple as the size of the data set, perhaps the average value of the data set, the number of each type of observation in the data set. For example, 5 blue, 6 green, etc. We may go a little bit deeper and talk about distributions. For example, is most of the data clustered around a certain value? Is it spread out? What does that spread look like? I'm keeping this a little bit general right now. I'm not using a lot of technical statistics words, but this is what we're talking about when we talk about descriptive statistics. So now let's put some definitions inside our two descriptive statistics. So the average value of a data set is usually called the mean, which is going to be challenging sometimes because you're not going to know when I say mean as in I mean this, or mean as in the average of a data set. Part of that's contextual, but I'll try to be clear. So for example, if I record a week of temperatures that are 68, 70, 72, 73, 70, and 56, and 80, 1, 2, 3, 4, 5, 6, and another 70 degrees, then I can find the average temperature for the week, called the mean temperature. Hey, by the way, Google Docs is pretty smart. It can actually do some basic math inside Google Docs itself. 417. That's not the average yet because I have to divide it by the number of observations. 417 divided by 7, which equals 59.571. So that's our average temperature. Now, different instructors, professors, statisticians may have different opinions on whether it's enough to say, or whether you should say 59.571 or 59.57 or 59.6. I consider that a judgment call. Your online homework will be specific about how many digits to use. Personally, I don't care. It's temperature. I don't know the difference between 59.57 degrees or 59.6 degrees. Now, if I were doing some very, very high level laser-based calculations of subatomic particles, then I would want to know. So the number of digits you round to is highly contextual. I just want you to keep that in mind. Another way to measure the average of a data set is to find the central value from the data. This is called the median. So if I take my week of temperatures, 68, 70, 73, 70, 56, 18, 70, I can find the central one by ordering them. Let's see. And then I just find the number that's right in the middle of my ordered list, which is 70. So the median temperature is 70 degrees. Okay. So that's the average value of observations in the data set. The size of the data set is hopefully more self-explanatory. The size of each of these data sets are 7. The number of type of each observation, the number of each type of observation for each observed value is called the frequency. Frequency is almost always used when exploring qualitative data, i.e. non-numerical data. I wouldn't average blue and green, but I can count the number of blues and I can count the number of greens. Distributions of data sets are often explored using visuals. The most common type of visual for continuous data is called a histogram. We're going to get into this more in a later lecture video. Describing how data is clustered or spread out. Relates to a statistical term called variance and standard deviation. We'll come back to that as well. I just want you to have these basic words. Okay, so that's our descriptive statistics. They describe data so we can understand that data better. Inferential statistics use data we collect to understand a larger population that we don't know about. For example, if I want to know the average temperature in June in Salem, it might be hard to sample or to measure every temperature every day in June, especially if I'm looking at the average temperature over a number of years. Instead, I collect a smaller sample of data and use that to estimate the data about the population along with a reasonable range about that estimate. The way we would phrase this is based on a sample of 7 days, my estimate for the average temperature in Salem in June is 72 degrees with a reasonable range from 66 degrees to 80 degrees, something like that. All right, that's our next topic, inferential statistics. Now I'm going to throw some key terms at you when doing key terms from statistical studies. These are also listed in your book. I just want to talk through them and give them some examples. We've got population. I'm going to write them all down, and then I'm going to come back and define and give examples. Sample, parameter, statistic, variable, and data. So the population is the collection of all possible respondents in a statistical study. We almost never ask every possible respondent. I should say, instead of ask, I should say measure. Sometimes we're asking people, but sometimes we're measuring things. So a respondent, as an aside, a respondent doesn't have to be a person. It could be a day, right? Or an hour, or a car tire if we're measuring tire pressure, etc. I like to think of population as what we want to learn about. but we don't have the resources to measure the whole population. In fact, the whole reason statistics exists is because we don't have resources to measure a whole population. If we wanted to know the likelihood that someone has the flu right at this very minute, and we had infinite resources, we could ask every single person in the world if they have the flu right at this minute, and we would know, and we wouldn't have to do any statistics. But we can't do that. And so instead, we use statistics along with a smaller group of respondents to make an estimate. And that group is called the sample. The collection of respondents who give a response to a statistical study. The sample is usually chosen by the researchers in a way that balances the resources they have available with the level of accuracy they need in order to make inferences about the population. Inferences is estimates, best guess, that relates to inferential statistics. Parameter is a number that describes the population. For example, this is easiest to describe an example, the average temperature in June. A statistic is a number that describes sample. For example, the average temperature in the 7 days that I actually measured the temperature. A statistic is used to estimate a parameter. We never expect that statistics are completely accurate. We always expect some error in our estimate, so we also report a reasonable range. Keep in mind that this course is called statistics, and there is also a narrow definition of statistics, numbers that we measure on samples. Okay. And then we've got a variable number that, actually, I'm going to go one step further. I'm going to add something else. So population is a collection of all possible respondents. Sample is a collection of respondents who give a response to statistical study. I like to go one more level, which is an observation, a single respondent. So a variable is a number that is measured on a single observation. For example, today it is 68 degrees. That's the variable, is temperature. And finally, data, the collection of measurements on the sample, or all the responses from the study. All right, let me give you an example. We want to know the average weight of house cats. Obviously, we can't go out and weigh every single house cat in the world, even if we just want to know the average weight of adult house cats in Salem. That is too much work. Right? We're not going to be able to find the money or the time to pay someone to weigh every adult's house cat in Salem. However, adult house cats in Salem is our population. The group that we want to know about, but we don't have enough resources to measure everyone. Instead, we collect a sample of 30 house cats. This is our sample. The observations that we measure in order to get an estimate for the whole population. A single observation would be Miss Princess, one of the house cats in our sample. That's our population sample observation. Now, the parameter is the mean weight of adult house cats in Salem. And here mean is average. If I am a veterinary clinic and I want to know what's the average weight of adult house cats in Salem because I want to know generally what their health status is like, then that would be something interesting that I'd like to know. The statistic is the mean weight of adult house cats in our sample of size 30. This would be called the sample mean. And the variable that we are measuring is the weight of an individual house cat. The data is the collection of 30 weights of the cats in the sample. I'm going to pause, get some water, and then I'll restart, and it will feel like no time has gone. All right, next topic. We talked about how we use a sample in order to understand a population. Let's talk about how to collect a sample. In my example here of the house cats, I just said we collect a sample of 30 house cats, but there are a lot of different ways to do that. Again, I'm going to list them out, and then I'll describe or define each one. So let's start with a gold standard, simple random sample. This is choose how many observations you want in your sample, then pick those observations completely randomly from the population. So if you want to think about it this way, think about a population. There might be, 10,000 house cats in Salem. Imagine giving each of those house cats a number from 1 to 10,000, and then using a random number generator to pick 30 random numbers out of those 10,000. That's what it means to pick those observations completely randomly. This method is not the easiest, not in reality. It's certainly easy to describe. It's not the easiest in reality, but it is mathematically guaranteed to be the best way to conduct statistics. Okay, the next one is stratified sampling. Suppose that there is an important characteristic in the population that you think will affect a parameter that you are estimating. So for example, males tend to weigh more than female cats. In a simple random sample, you might just completely by bad luck end up with mostly female cats. And you're going to underestimate the average cat weight. So with a stratified sample, you can include those characteristics by dividing the population according to the characteristic. This is called stratifying. Then sampling from within each subgroup to make sure that the characteristics are included in the sample. In our example, sample 15 male cats and 15 female cats. I'm adding that example here to the simple random sample. All right. So technically, this is a little bit not quite as guaranteed to be the best way. You could introduce something called bias, but it's often very important when you're studying populations that have these characteristics. Another way to sample is called a cluster sampling, a cluster sample. This method is used often when you have limited resources. So for example, Salem is a pretty big city, and if you're going to randomly choose 30 cats, you might end up driving all over the city. So instead, divide the city into sectors, let's say 100 sectors. Choose a simple random sample of the sectors. Sorry, let me start over. Be a little more general. Divide the population into clusters. Simple random sample the clusters. Then measure every observation in the clusters that you pick. So in our example, maybe you pick neighborhoods instead. Choose 10 neighborhoods at random, then measure every adult house cat in each of the neighborhoods. It's a lot less random than simple random sample, but generally it's a good balance. Now you only need 10 researchers. They go to each neighborhood, and then they're going to measure each adult house cat, and that's going to give you a pretty random sample. Okay. There's another way, systematic sampling, often used in a process, a sample generated by a process, like an assembly line. Right, if you're trying to measure faulty batteries, or figure out which batteries are going to be faulty, you could wait until you have all 10,000 batteries produced and then go in and randomly pick 100 of those. Or you could just pick batteries as they come off the line and measure those as they go. So imagine lining up the population from 1 to 10,000, then picking every 100th observation to measure. As long as the arranging of the population is random, then the sample will probably be random. Again, not quite as random as a simple random sample, but pretty efficient if you have a process. So suppose you're going to weigh or collect the weight of every 100th cat that comes to your vet clinic. As long as those cats are not, or as long as those cats are coming in kind of at random times, then you're going to have a random sample. All right, so we've kind of been working from the gold standard, simple random sample. Stratified sampling I would put up there because there are often characteristics that are really important, and you want to make sure you don't miss them. Cluster and systematic samples, balance resources with quality of your sample, and then our low standard that is highly efficient with resources, very concerning from a statistical standpoint, is the convenience sample. Just choose whichever observations are convenient for you. And maybe you can kind of put some rationale, like I live in a neighborhood where I think the cats are representative of all the cats in Salem. But ultimately, you're saying, I don't have a lot of resources. I'm just going to pick whatever observations are most convenient, and I'm going to measure them. So example, weigh all the cats in your apartment complex and use those cats as your sample. Now, if you're lucky, those cats are representative of all house cats in Salem. But if you're unlucky, like say you have a neighbor who likes to feed all the raccoons, and so they always leave extra cat food out, so all the cats in your neighborhood are overeating, then you're going to get some bad data. This method is not recommended by statisticians, but is often used because, it's often used because the other methods are too resource expensive. All right, so those are the types of samples. Just a couple more topics in this lecture video. Again, I know these are long. I hope you've been taking pauses, taking breaks, just like I have been. Bias and studies. So statistical bias is the let me say it this way, avoiding statistical bias is the primary role of a statistician when creating a sample. Bias means a recurring tendency to misestimate, I don't know if that's the word, Google doesn't mind, to misestimate the parameter to misestimate the parameter, usually because the sample was not representative of the population. So let me give you an example. Here we go. I did give you one. You sample the cats in your apartment complex, but someone is always leaving extra cat food out, so the average weight in your apartment complex consistently overestimates the average weight of house cats in Salem. Looking back at our sampling methods, Least likely to have bias is a simple random sample. Next least likely is the stratified sampling. Cluster and systematic samples have a higher risk of bias, and convenience samples have a high risk of bias. Ways to overcome the risk of bias. Now, one of the challenging things in statistics is we don't know if we have biased data. Biased data means our sample is not a good estimate of our population, but the whole point of statistics is we don't know what our population is. So we can't necessarily overcome bias, but we can minimize the risk. Let me say it that way, minimize the risk of bias. Step one, which is the gold standard, is sample randomly. The more random your sample is, the less the risk of bias. Another way is you can increase your sample size. As an example, 15 male cats and 15 female cats compared to 30 male cats and 30 female cats. Now, you're going to have a lower risk of bias if you pick 30 and 30 than if you pick 15 and 15. Those are generally the biggest ways to minimize the risk of bias. There are some other statistical methods that we won't talk about, like weights, oversampling, etc. Okay. All right. Last topic, and it also comes from sampling. It's called sampling with replacement versus without replacement. So mathematical statistics says that the best estimate of a population comes from a sample that is drawn completely randomly, which technically means that the same observation could be included more than once. Example, pick a cat, weigh it, let it go. Pick another cat, weigh it, let it go. Now there's a possibility that at some point you pick the same cat. Mathematically, that's the best way to get an estimate of your population. But in the real world, it's pretty unreasonable. This is called sampling with replacement, because you replace the observation in the population and could sample it again. The way we actually do most of our statistics is called sampling without replacement. In this case, you would pick 30 cats, weigh all of them. Notice that in that sample of 30, you definitely don't have any repeats, because you picked your 30 cats before you weigh them. This is generally how we collect samples. If you think about interviews or surveys, and you end up calling the same person 4 times, they're going to be pretty irritated with you. If we're sampling batteries, we're probably not going to pick the same battery more than once, because that doesn't really give us more information. Mathematically, if we sample without replacement, there's a small chance that we're introducing some bias. However, in general, sampling with replacement is fine as long as the population size is much bigger than the sample size. Sampling 30 cats out of the 10,000 in Salem is fine. But Let's see. Sampling 30 cats without replacement out of the 10,000 in Salem is fine. But sampling, let's say, 30 donkeys out of the 70 donkeys in Salem, sampling 30 donkeys without replacement out of the 70 donkeys in Salem runs the risk of introducing bias. So most of our studies that we look at, most of the time you collect data that's observational, you're going to be sampling without replacement. Let's just say this. I misspoke. Sampling without replacement is fine as long as the population size is much bigger than the sample size. So that's the end of the lecture 1 notes. Go back and watch this again as you want. This should prepare you to start on your homework. It should give you some information that will help you with your Lab 1, although Lab 1 is focused more on the content from Chapter 2. Thanks for bearing with me, and I'll see you next time.